Okay, we can see it
Is everything
very well.
okay?
Yeah, it's perfect. So now we continue with today's last talk. Who is going to talk is Vinicius Justen Pinto. He's a student from UFRJ from Rio de Janeiro, Brazil. And he's going to talk about the Van der Pol equation, qualitative and numerical study. So Vinicius.
Okay. So I'm Vinicius, undergraduate student in electrical engineering at the Federal University of Rio de Janeiro. My advisor is Professor Luciana Salgado, and this presentation is part of the scientific initiation program. So we begin the presentation with a historical background and some applications to this equation. We'll deduce the Van der Pol equation, state some theorems that will be used in the qualitative analysis, and we also make analytical approximations. And at the end, we make a numerical analysis. Balthasar Van der Pol was a Dutch physicist, pioneering radio communication, with contributions on engineering and on mathematics. And in 1926, he published his paper entitled On Relaxation Oscillation, on relaxation oscillations, introducing what we now call the Van der Pol equation. Some applications are electrical oscillators, mechanical system, the Tantalus cup, the heartbeat, Parkinson tremors, and many other phenomena. The deduction, we utilize this concept model, which is an oscillator circuit. This is a controlled current source controlled by voltage. We have a capacitor and an inductor. These are the currents through each component. And we apply the Kirchhoff's current law in this node. And the Kirchhoff's current law is an application of the conservation of charge in electrical oscillators, in electrical circuits. And we can derive the Van der Pol equation. We can deduce the Van der Pol equation in its normalized form. We can write this equation as a Leonard system. And this system will be used in our analysis here. So we consider this nonlinear system with an equilibrium point XO. An equilibrium point is said to be locally stable in sense of Yapnov if in the neighborhood of this point, all trajectories stay close to this point. An equilibrium point is said to be locally asymptotically stable if in the neighborhood of this point, all trajectories tend to this point as time tends to infinity. The omega limit set is the accumulation of points with a sequence tk going to infinity. And an alpha limit set is defined the same way, but with the sequence tk going to minus infinity. The Yapnov's indirect method considers the linearization of a system in order to study its local stability. So if the linearization exists, its stability implies local stability for the original nonlinear system. A system can be linearized by the Jacobian matrix, and analyzing the eigenvalues of this matrix, if the real part of the eigenvalues is positive, the equilibrium point is locally unstable. If the real part of the eigenvalues is negative, the equilibrium point is locally stable. And for eigenvalues equal to 0, this linear approximation is not sufficient to determine the equilibrium state of the system. But this case does not occur analyzing the Van der Pol equation. Studying a linear system, it is important to check if the omega limit set has periodic solutions, which are the limit cycles, and they can be classified with respect to stability as asymptotically stable if all neighboring trajectories approach the limit cycle as time approaches infinity, unstable if this happens as time approaches minus infinity, and semi-stable if one trajectory approaches the limit cycle as time approaches infinity and the other as time approaches minus infinity. The Poincaré-Bendixsen's theorem considers an open set subset of R2 and a vector field of class C1 with a finite number of equilibrium points. And if a point P is so that the positive trajectory is contained in a compact set of this open set, If the omega limit set contains only equilibrium points, then it consists of a single equilibrium point. If it contains only regular points, then the omega limit set consists of a single closed trajectory. And if the omega limit set consists of equilibrium points and regular trajectories, then in the future, in the past, all trajectories tend to equilibrium points. Yapnov's direct method is a generalization of an energy function, and the idea is to find candidates to the Yapnov function and then analyze its behavior. The Yapnov function considers a vector field in an open set subset of Rn, and XO is an equilibrium point with a neighborhood A. So V is a Lyapunov function if applied to the equilibrium point is equal to 0, and in the neighborhood of this point is positive, and if it is a non-increasing function. The Lyapunov's stability theorem says that if the Lyapunov function is non-increasing, the equilibrium point is stable, and if it is strictly decreasing, the equilibrium point is asymptotically stable. Now we begin the qualitative, we begin with a general analysis. This is our equation, the van der Pol equation. And if we consider an initial point to be of small value of x, we can rewrite this, we can neglect this quadratic part, and we rewrite the van der Pol equation as this linear equation. And we can find the solutions. For negative epsilon, the damping term is positive, and the solutions have a decreasing behavior towards the origin. For positive epsilon, the damping term is negative, and the solutions could a priori increase indefinitely, but this is not what happens, because when x becomes sufficiently greater than 1, this constant part may be neglected, and we write the equation as this equation here. Now the damping term for positive epsilon is positive, so this limits the growth of x. And for negative epsilon, in the situation with an x sufficiently greater than 1, the damping term is negative, and since there is no limiting term, the solutions do grow indefinitely. So this general analysis indicates that for negative epsilon, there should be an attracting term to the origin, which is a stable equilibrium point, and a repulsive one depending on the initial conditions. And for positive epsilon, there should be there should exist a repelling factor around the origin in an asymptotically stable limit cycle. Now, applying the theorems, this is the indirect method. Here we have our system. And we can see that the only equilibrium point is the origin. So the Jacobian matrix applied at this point is this matrix here, and we can find the eigenvalues, which are given by this relation. And here we can see that for negative epsilon, the real part of the eigenvalues is negative. For negative epsilon, the real part of the eigenvalues is negative. So the origin is locally stable. For positive epsilon, the real part of the eigenvalues is positive, so the origin is locally unstable. And for epsilon equal to 0, our equation reduces to a linear equation with solutions of this cosine form, where phi and Na are constants determined only by the initial conditions. So this shows the dependence on the amplitude of the oscillations with the initial conditions of the system. Before applying the Poincare-Abel-Dixon's theorem, it is important to know the behavior of the derivatives, both in polar and Cartesian coordinates. So here we change variables, and after some calculations, we achieve the system, the van der Pol system in polar coordinates. And here we'll analyze this first equation, which is the first time derivative of the radius. And here we can see that for negative epsilon, in the neighborhood of the origin, the radius decreases. So there's an attracting factor here to the origin. And outside this neighborhood, the radius increases. Whereas for positive epsilon, it is the other way around. The radius increases in the neighborhood of the origin. So there's this repelling factor here. And outside, the radius decreases. Now analyzing the derivatives in Cartesian coordinates, we can call this part of the function a f of x. And f of x is represented here by those blue curves. If a point is above f of x, its x coordinate is increasing. If it is below, x decreases. And for y equal to f of x, the x is constant. If x is positive, y is decreasing. If x is negative, y increases. And for x equal to 0, y is constant. So this analysis, after this analysis, we can say that for a negative epsilon, all trajectories with an initial condition in a neighborhood of the origin tend to this point. So the omega limit, the origin is an omega limit point, and therefore, using the Poincare-Eben-Dixon's theorem, we say that the omega limit set consists of a single equilibrium point. And for positive epsilon, all trajectories with initial conditions in a neighborhood of the origin go out towards the origin. So the omega limit set contains only regular points, and therefore it consists of a single closed trajectory, which is the limit cycle. Here we used a method of the variable gradient in order to find a candidate, a Yapnov function candidate, which is this function here. And we can see that the first condition of the definition of the Yapnov function is easily satisfied if we let C1 and C4 positive, because V applied to 0 is equal to 0, applied to the origin, sorry, which is our equilibrium point, is equal to 0, and outside the origin is positive. And if we let C1 equal to C4, this is the first time derivative of the Yapnov function. And it is a similar relation compared to the first time derivative of the radius, which we saw previously. So letting this domain D here, we can study this relation, the time derivative of the Yapnov function. And for negative epsilon, the Yapnov function inside this domain is strictly decreasing, so the origin is asymptotically stable. But for positive epsilon, this happens outside our domain D, and inside this domain, V is strictly positive. So since we know that there exists a limit cycle, this behavior shows that the regular trajectories are asymptotically stable. Now some approximations. First, we consider weak nonlinear oscillations, which are epsilon sufficiently smaller than 1. And this is the approximate solutions. This is the approximate solution, where A is a function of time, slowly and varies slowly. So we can represent we can use the Van der Waals system in polar coordinates in order to find this relation of A with respect to time, which is this relation. And after and this is the general solution for small epsilon, applying A to the general solution, where C is a constant of integration. And here you can see that for positive epsilon, as time approaches infinity, this denominator tends to 1, and the amplitude in the steady state, the amplitude of the oscillation in the steady state is equal to 2. without not mattering the initial conditions. But for positive for this parameter epsilon sufficiently large, this equation does not hold, but we can still study the system's behavior over time. We let this change a variable, and we call a g of x this polynomial here, and we rewrite the system as the system. And we analyze it in a similar way as we made previously, but now we are tending epsilon to infinity. So if y1 minus g of x is, let's say, of order 1 or greater, the time dot x also tend to infinity as epsilon tend to infinity, and dot y1 tends to 0. But if y1 minus g of x is of order epsilon, the dot x does not tend to infinity. So this is the idea that we used to generate this sketch. First, we considered an initial point sufficiently apart from g of x in the y1 direction. So initially the trajectory is almost horizontal, and it is a fast trajectory. Then after it reaches this region nearby g of x, it stays close to g of x with an order of 1 over epsilon. So the trajectory becomes slow. Then we have another fast trajectory, another slow trajectory, another fast trajectory, and this idea of a fast trajectory followed by a slow trajectory is what gives this type of oscillations the name relaxation oscillation. And here we saw this limit cycle being formed. Points A, B, C, and D are easily calculated using g of x, and we can use this idea of a relaxation oscillation in order to estimate the period of these oscillations, because we can neglect the fast trajectories to the contribution of the time, and we integrate from the time from point A to point B, and this is half of the period. This is what is shown here. And using the system, we can change this integral with respect to time to an integral with respect to x, because we know points. I'm sorry, there's a little bit of noise here. So we know points xa and xb, so we can integrate in order to find the period, and the period is given by this relation with an error of order 1 over epsilon, and we have to keep in mind that we are considering epsilon sufficiently large. This is a sketch of the temporal behavior of a relaxation oscillation. This is an animated plot made using Octave. And this shows the time difference between those two trajectories, the fast one and the slow one. Here we have the temporal behavior. And finally, the numerical study. We integrated numerically the Vanderpool system using Octave and Python. And we used this in order to illustrate the analysis made until now. For the phase portrait, considering a negative epsilon, we see the attracting factor around a neighborhood of the origin. And outside this neighborhood, the solutions grow indefinitely. And for positive epsilon, we can see that there exists a limit cycle asymptotically stable, because with initial conditions inside and outside this periodic solution, the trajectories tend to the limit cycle. For epsilon equal to 0, we see that the amplitude of the oscillation is determined only by the initial conditions. The temporal behavior expressed here, for epsilon sufficiently small, there is this transient part, and in the steady state, the amplitude is approximately equal to 2. And if we let epsilon sufficiently large, we see the relaxation, the typical relaxation oscillation behavior over time. And finally, these are two basins of attraction. The one trapped inside this red rectangle we obtained using our Yapnov function, and this blue one was made using Octave, and the algorithm tests the points, initial points, and see if the origin is an omega limit point. Because if it is, the initial condition is inside the basin of attraction, and after the algorithm tests for a certain number of initial conditions, we can plot the initial conditions in order to form the basins of attraction, the basin of attraction. These are the references used in this presentation. And thank you so much for watching.
Thank you, Vinicius. Are there any questions? If not, I have one question, but it has to be with the very first thing that you said, I think, which are the applications of this type of equations. You mentioned that it can be applied to Parkinson's.
Oh, sorry, I was mute.
Okay.
Yes, there were some researchers that modeled the Parkinson tremors with the van der Pol equation in order to study if they could, in a certain way, diminish the tremors.
Nice.
And I'll show the reference, please.
Yeah, please. It's very interesting.
Here, this.
Parkinson and tremors. Okay, thank you.
Yes, there were other researchers, recent researchers, also studying the Parkinson tremors as with the van der Pol equation.
Okay, thank you. And the other question that I had is, you're an engineer, right? You're a graduate student from engineer.
Yes.
So how has been this experience working with Luciana, who is a mathematician, and all this work?
Yes, I'm a little bit scared of mathematics.
Don't say it.
I'm saying it again.
Okay.
I'm sorry.
Okay, you can go on. You can go on. I'm permitted.
But it is pretty much fun, because we began, I think, 2 years ago, and now with more advanced in the engineering, in the undergraduate study in engineering, we applied much of this theorems to study the control theory in electrical engineering. So it is interesting to see it again, now viewed as a more engineer way, in a more engineer way.
So I'm glad that you turned to the dark side, as they say.
Okay, I got it.
I don't know if anyone has any other question. Okay, if not, let's thank Vinicius again. Thank you very much for your presentation. Luciana, thank you again, you too. I think Yaya is, there is Yaya. Thank you, Yaya.
Thank you. Thank you.
Thank you. Thank you.
So we are actually ended from today. We continue this session tomorrow at 8 with the modeling part, more applied part. And I think at 11, we have a plenary talk from Kristen, who is a cryptographer from the US. It's a very interesting presentation. So I invite you all to attend it. And let's see you tomorrow. Thank you very much for being here.
Thank you.
Thank you.
Good to see you.
Thank you.
Bye.
Good to
Nice
see
to
you
see you
also.
all.
Yeah,
Bye-bye.
talk to.
Ciao, ciao.
Nice to meet you.
Ciao. Okay.
Ciao.
Ciao.